Let's consider an example where we're going to compute the probabilities of both a type 1 and a type 2 error occurring. Consider a political poll regarding the opinions of a random sample of 15 voters in their preference for candidate A versus candidate B. And let's define the null hypothesis to be theta is equal to 0.5 versus the alternative hypothesis that theta is less than 0.5. In this case, remember, since we're working with a binomial random variable, this theta is the parameter that represents the probability of success, which is 0.5. So what we're saying here, then, is that the true population proportion of voters who prefer candidate A is 50%. Now let's define the test statistic y to be the number of sampled voters who favor candidate A, and suppose we would define the rejection region for this hypothesis test as the set of y values that are less than or equal to 2. And our first task in this example will be to find alpha, the probability of a type 1 error, and we'll follow that up with finding beta, the probability of a type 2 error, specifically in the case when the true population proportion is equal to 0.3. So alpha, remember, is the probability of a type 1 error. And a type 1 error is when we reject the null hypothesis when in fact it's true. That corresponds to our y value being in the rejection region while the null hypothesis is true. So that means for us, our alpha is equal to the probability that y is less than or equal to 2, that's what it means to be in the rejection region, given that theta is equal to 0.5 as hypothesized by the null hypothesis. Now since y is binomial, we have the first parameter n is 15 and the second parameter theta is equal to 0.5. So alpha equal to the probability that y is less than or equal to 2 given theta equal to 0.5, then we can compute by using the binomial distribution. This becomes the sum as y goes from 0 to 2 of 15 choose y times the probability of success raised to the y power times the probability of failure raised to the 15 minus y power. We can do a little bit of algebra to rewrite this. If we do, it makes it easier to compute, and our probability ends up being 0.004. So that's a very small probability of a type 1 error. Effectively, what it means is if we use our rejection region where y is the set of values less than or equal to 2, we subject ourselves to a very small risk of concluding that candidate A will lose if in fact candidate A is the winner. Now let's determine whether or not our test is equally good in protecting us from concluding that candidate A wins if in fact A loses. In other words, suppose candidate A receives 30% of the vote. Now let's find beta. Since beta is our probability of a type 2 error, that means we're interested in the probability that we fail to reject the null hypothesis when in fact it should be rejected. That's equivalent to saying that our y is not in the rejection region while the alternative hypothesis is true. And in this case, remember, our alternative hypothesis stated that theta was strictly less than 0.5, but in order to compute this probability, we need to know the true value, and in this case, we're going to say that the true value of theta is 0.3. So we're looking for the probability that y is greater than 2, because that's not in the rejection region, given that theta is equal to 0.3. And that's equal to 1 minus the probability that y is in the rejection region while theta is equal to 0.3. And we can use our probability distribution again to compute this probability. If we do, we get 0.873. So that says that there's an 87.3% chance that we're going to make a type 2 error. In other words, if we use this particular rejection region that says we're looking at the set of y values less than or equal to 2, our test will almost always lead us to conclude that candidate A is the winner, even if theta is as low as 0.3. So a few remarks here. In that last example, we might notice that the value of beta depends entirely upon the true value of the parameter theta. And it's also worth noting that the larger the difference between the true value of theta and the hypothesized value of theta, which was given in our null hypothesis, the smaller the likelihood that we will fail to reject the null hypothesis. In particular, suppose the true value of my parameter is equal to 0.1, which is even a greater difference between that and the hypothesized value than our previous example. If we then go to try to produce the probability of a type 2 error, we discover that we get an even smaller probability of 0.184. It's also worth noting that we can balance the probabilities of a type 1 and type 2 error by changing our rejection region. If we enlarge the rejection region, that results in rejecting the null hypothesis more often. In other words, the probability of a type 1 error increases. This also means that we will fail to reject the null hypothesis less often. Therefore, the probability of a type 2 error decreases. So for a fixed sample size, the probability of a type 1 error and the probability of a type 2 error are inversely related. But it is worth knowing that we can reduce both probabilities of a type 1 and a type 2 error by increasing our sample size.